the change of base rule, example 1. Find logarithm in base 2 of 9 by 3 different ways. So in part A, we have to let logarithm in base 2 of 9 be equal to some value of y. So this is what I'm going to do in this part. So I want to find the logarithm in base 2 of 9. So I don't know what it is, so let me denote the unknown value by the variable or the unknown y. Now, if I have this equation, I can replace it by the equivalent exponential equation. So this is equivalent to saying that 2 to the power of y equals 9. And the reason is, as you already know, the meaning of the logarithm. The logarithm is such an exponent, the exponent with the property that if you raise the base to this exponent, you should get the number from which you took the logarithm of. So this is the equation, and now I can use decimal logarithms to take a logarithm from both from its left hand side and right hand side. So on the left hand side I get a logarithm in base 10, of course, of 2 to the power of y, and this equals the logarithm in base 10 of 9. Now, using the third or the power rule law of logarithms, I can say that the left hand side equals y times the logarithm of 2 in base 10 equals a logarithm of 9. And now I can express the value y by dividing this equation by logarithm of 2. So y should be equal to logarithm of 9 divided by logarithm of 2. And this value here, which I expressed in this way, is actually the same as this value here, which was the original logarithm in base 2 of 9. So if I want to calculate the logarithm in base 2 of 9, I have to calculate this fraction. This fraction is calculated simply using the calculator, so I just type in logarithm of 9. What I get is the number 0.9542. This is just approximate, so let me replace equals sign by approximately equal sign, divided by, and if I take the logarithm of 2, the decimal logarithm of 2, what I get is the number 0.3010, and this then approximately equals to, so I just divide these two numbers, so it's 0.9542 divided by 0.3010, and what I get is an approximate value of 3.17. I can write another 0 there. So this is the approximation of the logarithm in base 2 of 9. Now in part B, the same calculation should be achieved in a different way. So we have to express the logarithm in base 2 of 9 using the change of base rule. So if I use the change of the base rule directly, what I get is the following. It's the logarithm of 9, it's the logarithm of this number here, divided by the logarithm of the number down there below. So it's the logarithm of 2. And you see, this is exactly the same expression as the one obtained in part A, so I don't have to bother with typing this into my calculator. What I can write directly is the answer is approximately 3.170, like that. In part C, we have to change to base E. So if I do that in part C, I can express the logarithm in base 2 of 9 using the change of the base rule as the natural logarithm of 9 divided by the natural logarithm of 2. Okay, so this is both this one and this one are logarithms in base e. So I use the abbreviation. I don't write logarithm base e, but I just write logarithm. And now this can be approximated. So again, I'm going to use my calculator, but this time I'm going to use the key which is denoted as ln. So it's the natural logarithm of 9, which is the number 2.1972 divided by, and the natural logarithm of 2, which should be 0.6931, and this approximately equals to, and now again, 2.1972 divided by 0.6931 equals, and what I get is 3.170 as the answer, as the approximate answer. So this is how you calculate logarithm in base 2 if you have only a calculator which doesn't have a special key for calculating logarithms in base 2. So that's why you need something like the change of the base rule to be able to calculate also the logarithms in other bases.